You've probably been wondering all semester what was the purpose of the baking analogies, and there were two. First, they were designed to give you a more tactile realization of vectors, linear combinations and span, stuff like that. Second, I wanted you to start thinking outside of Rn. Clearly, flour isn't what you think of as a vector. It lacks a magnitude and direction. However, cookie ingredients do behave similar to vectors in Rn. We add them together by mixing them, and scalar multiples are just more of the ingredient. We are going to move away from vectors in Rn to just vectors. We're going to steal all the nice properties from vectors in Rn and explore different structures with these same properties. Cookie ingredients is a good motivation for this, but is actually a terrible analogy for several reasons. The biggest is the scalar multiple being negative. It's moderately difficult to add -1 egg to a recipe. Here's a definition. A vector space is a non-empty set V so that the following hold for all u, v, w, and v, and scalars a and b. First, if you add two vectors together, the result is still in V. Second, it doesn't matter what order we add the vectors, so u plus v is equal to v plus u. Third is associativity. It doesn't matter what operation we perform first. Fourth, the vector space must contain 0. Fifth, all vectors have a negative. Sixth, any scalar multiple of a vector is still a vector. Seventh, scalars distribute over vector sums. Eighth, vectors distribute over scalar sums. Ninth, scalar multiplication is associative. 10th, the scalar 1 doesn't change the vector. 11th, there's only 10. If I ask you to show something as a vector space, that is a 10-part problem. Elements of vector spaces are called vectors. If I say something is a vector, that means it lives in some vector space, and that vector space satisfies all 10 of these properties. If you're having a mild panic attack and are desperately missing Rn, let me give you some good news. We're going to work very hard to represent all finite dimensional vector spaces as a copy of Rn. That means the only finite dimensional vector spaces are just copies of Rn. Does the word finite have you worried? Does finite make you think we may eventually discuss something bigger than finite? Like infinite? Let's do an example showing something as a vector space. Let Pn denote the set of polynomials with degree at most n. Show Pn is a vector space. Before we start, we need to determine what elements of Pn look like. A general element of Pn is a polynomial. And we know what a polynomial is. It looks like a0 plus a1x plus a2x squared up to an x to the n. Notice we stopped at degree n, because all polynomials in Pn have degree at most n. As emphasis, x squared is in P3, x cubed is in P3, but x to the fourth is not in P3, since 4 is not less than or equal to 3. To set up our proof, let's pick 3 arbitrary vectors from Pn, call them f, g, and h. I used e's and h since I'll use c and d for scalars. Now we need to show all 10 of those properties. Just go one property at a time. First, add two vectors together. Combine like terms, and we see the result is still a polynomial with degree less than or equal to n. Note, the degree could be smaller than f or g, but that's fine because it's still less than n. Second, add two vectors, combine like terms, the ai's and bi's are scalars so they commute, re-expand and separate, so the vectors commute. Third, associativity. This is going to be a long one. Take it one step at a time and do not skip steps. Your goal is to convince anybody that this is true. But it is. Fourth, 0 is a polynomial, and here's a fun fact. The degree of the 0 polynomial is negative infinity. Figure that one out. Fifth, negative f of x is just negative f of x. We should check that when we add these together we get 0, and we do. Sixth, a scalar times a polynomial. Just distribute. Each coefficient is a real number. Cool, it's a polynomial. Seventh, distribution. Just remember to not skip steps. That's the most important part. Eighth, another distribution, and yep, it works. Ninth, another associativity. Again, distribute and group. 10th, 1 times a polynomial is just the polynomial. And we're done. It's over. Pn is a vector space. Fortunately, this class has timed exams. I can only ask you to do like 4 or 5 of these on an exam.